morning everybody. So, today we will continue with kinetics of some specific reaction, and under this heading we will start with acids, bases and metal ion catalysis. So, the mechanism goes as it's a general mechanism like this, that B minus, and this is your acid, then this is your acid, means HA, it is an acid. So, this consists of 3 steps primarily, that is this is your substrate, or maybe this is a base also. So, which abstracts the proton from this acid, and during abstractions, means to do this abstraction, it should follow, or it is postulated to follow such scheme. Now, here what happens is that there is a bond formation. Okay, there is a bond formation which is a hydrogen bond formation between this base and this acid, and then what happens that this bond, this HA bond stretches, and this hydrogen bond, this length squeezes, and as a result of which basically this hydrogen is shifting its position from this region to this region. I mean, it is moving this way, and ultimately there is a bond formation between B and H, and this bond cleaves, resulting in A minus. Okay, and BH is, or basically since we started with B minus, so BH neutral has been formed. So to deal with acid base catalysis, we should know means how these acids are acting. Okay, now acid means it is basically a proton. Okay, so for this proton to act as a catalyst, so the following scheme may be useful. Now, basically A is diffusion controlled hydrogen bond formation, then it is a proton transfer. This second step is the proton transfer, and then the last step is your dissociation, that is dissociation of original HA bond. Okay. Now, diffusion controlled means this formation of this complex, I mean BHA complex, requires that this interacting substrates should come close to each other, and since it is coming close to each other, it occurs by the process of diffusion inside the solvent. Okay. So, it swims close to this B minus. So, 3 steps for this such type of catalysis, acid base catalysis. So, diffusion controlled hydrogen bond formation, proton transfer, that is PT, and dissociation. Now, faster proton transfer has been found to occur with this nitrogen, oxygen or sulfur. So, this B minus, okay, if the interacting group or interacting atom in B is having nitrogen, oxygen or sulfur, that is the atom which interacts with this hydrogen to form a hydrogen bond. If it is nitrogen, oxygen or sulfur, then this proton transfer has been found to be very fast. If it is carbon, okay, then it is slow, and proton transfer from hydronium ion H3O plus to nitrogen and oxygen, it is diffusion controlled. Okay, it is very fast. So, basically it depends on how how fast these interacting substances are coming close to each other. So, and that is limited by the diffusion of them, diffusion that is how they are diffusing close to each other. Okay, that is why it is called a diffusion control, and the rate is 10 to the power 11 liter mole inverse second inverse, very fast. Okay. So, you see that AH, it is an acid, here H2 is the base, forward reaction, the formation of A minus and H3O plus. Okay, and the back reaction is the back hydrogen or back proton transfer to give you AH. Okay. So, this is your acid, its corresponding ion, this is base corresponding H3O plus. Okay. So, hydrogen bond formation between proton donor and proton acceptor. So, this one is proton donor and this one is proton acceptor is the rate determining step. Diffusion of proton in water is very fast compared to diffusion of other ions. Why? Because proton is very small in size, okay, and as a result of which and also there is a mechanism which is called, it is a Grothus type mechanism, by which basically proton does not need to swim close to your interacting entity. What happens is that it is basically a relay kind of mechanism that one side this proton is attaching, next side another proton is detaching. So, in this way this proton is attaching over here, say at one point. So, next point the other proton is detached to another point. So, basically all the proton has attached to this point, but effectively the other proton which has been detached has attached to another side. So, basically it is a two step, although in order that the original proton required more time to attach to here, because it needed to swim to this position. Okay. So, that is why it is a relay kind of mechanism. So, it looks like this. Suppose you have got water, okay. So, there is another water, okay, and you have got one proton. So, the lone pair, so it attaches over here, this lone pair is snatching this. So, another lone pair is snatching this. So, effectively this hydrogen bond or this bond has been formed, but see this proton as if has moved to this position. So, it is a kind of push pull kind of mechanism. It is also called the Grothus type of mechanism. Okay. So, that is why it is very fast compared to diffusion of other ions, because for other ions, since it is for proton it is the lightest entity. Okay. So, lightest entity means it does not require that much of time to move, and also if this mechanism is operative, then it is even faster. But for other ions, since they are heavier and also maybe because of solvation they become larger in size. So, what happens that in order for them to diffuse, okay, in order to diffuse from one position to another, they would require more time. So, that is why diffusion of proton in water is very fast compared to diffusion of other ions. Okay. Now, see it is basically an ion, as I told you that here it is also shown in the same way why it is faster, that you have got A minus, okay, which attaches to this proton, and then this bond is broken and is given to here, and then what happens that this original this OH bond, O plus H bond is now broken. So, effectively this proton has been taken from here, but effectively as if the proton from here has been taken. So, net there is a two step jump, although for other ions like say heavier ions this does not happen. Okay. So, this way this is for an acid, and for base you see that OH minus, it is snatching this proton, and effectively as if this proton has been snatched through this water hydrogen bonding. Okay, that is why this is very fast, and also since proton is the lightest entity, therefore they do not take that much of time to diffuse from one place to another. Proton transfer involving carbon acid or carbon bases. One example is given here, that CH3CH2NO2. So, water forward reaction. So, forward reaction is basically this hydrogen has been taken, okay, this hydrogen is taken and H2 plus is generated, and then it's a resonance hybrid of these two. So, effectively what happens that all there is a C minus, now it is converted to an O minus. Okay. So, initially it was a carbon acid, now maybe it is converted to oxygen acid maybe. Okay. So, it looks like as if this hydrogen has been taken from here. Okay. Another example is like this, CH3CO CH2 CO CH3. So, forward reaction, I mean forward process, you see that it is enolization step. Okay. So, and it is your enolate. Okay. So, basically this hydrogen is given to here, I mean this hydrogen is switched from here to here. Okay. 1 2 3 1 3 shift. So, making this double bond, then OH, and then this OH, what happens that this OH makes a hydrogen bonded structure, I mean 6-membered hydrogen bonded structure. So, although this is slower, but this process, I mean this process is faster, the forward process is slower, but from here to here this back process is faster, and also this forward process is faster because you see that these two are carbon acid. Okay. And these 2 to 3, it is an oxy acid, oxygen acid. So, therefore, this process is faster, probably because of this hydrogen bond formation. So, hydrogen bond makes the process faster compared to when there was no hydrogen bond. Okay. So, here it is the proton transfer involving, I mean carbon, it is the proton transfer involving oxygen. So, it is an oxygen acid, this is a carbon acid. So, slow proton transfer, and here it is the fast proton transfer. As I told you, here proton transfer, nitrogen, oxygen, sulfur is faster compared to carbon. Now, we will now concentrate on to the effect of pH on reaction rate, since it is a hydrogen mediated, I mean hydrogen plus proton mediated, I mean proton catalyzed reaction, or maybe Witch minus catalyzed reaction. Okay. So, let us look into hydrolysis of ester catalyzed by both acids and bases. So, in one case let us concentrate on to acid catalyzed, in the other case concentrate on to base catalyzed. So, acid catalyzed reaction. Okay. So, you see that this one, okay, CH3CO OCH3. So, protonation, protonated form, it is the protonated form, acid catalyzed reaction. So, in presence of water, it is a tetrahedral intermediate is formed, and then backfiring of this OH electron, OH pair, then expels this CH3OH. Okay, CH3OH means it is methanol. So, it is the acid catalyzed prescription. What about the base catalyzed prescription? You start with CH3COOCH3, and water, in presence of water and also in presence of a base. So, this in presence of water, this tetrahedral intermediate is formed, and then OH minus attacks, then this one is expelled as OCH3 minus. Okay. So, then it is CH3OOCOOH. Okay. Now, then in presence of water, I mean this is the equilibrium has been shifted from CH3O minus to CH3OH and CH3COO minus. So, but it is a base catalyzed prescription. Okay. And if we plot logarithm of K observed rate constant as a function of pH, approximately the rate is found to be, I mean it is found that at pH 7, that is at neutral pH, its rate is minimum. So, either if it is increased this way, I mean if it is going this way, acidic region or maybe in the basic region, so the reaction rate is increasing. Okay. So, this particular reaction, that is particular reaction means the acid catalyzed or base catalyzed hydrolysis of ester. So, when pH is 7, that is the neutral pH, it is the minimum rate, and if you go either way, whether you increase the pH or whether you increase the decrease the pH, rate is increased because it follows such a mechanism, because it has got two options, that is acid catalyzed option or maybe the base catalyzed option. Okay. So, both way, if you go this way or that way, the rate of reaction increases. Okay. Thus, we can see that there is a great deal of effect of pH on such kind of reaction. Next, another example is an interesting example, mutarotation of glucose. So, it is cyclic form of glucose. Now, if it is acid catalyzed reaction, then we see that this is the prescription. This is for uncatalyzed one, this is catalyzed prescription, and this is base catalyzed prescription. Now, if we plot log K observed versus pH, then around neutral pH the rate is minimum, okay, and not exactly at 7, but around pH 7. Okay. Now, so for a region, for some range of pH in the vicinity of 7, it is flat, and then it increases this way also and also this way because of this mechanism. So, this is ring opening reaction, that is 6 membered closed structure to an open structure, and this is at acid catalyzed mode, this is uncatalyzed, and this is very slow. Okay, this is very slow, and this one is base catalyzed one, because importantly, you see here this OH minus snatches this proton from this anomeric carbon, and then this carbonyl bond is formed, and then this is open here. Since there is no such OH minus or maybe no such proton, because it is at pH around 7, uncatalyzed means around 7. So, in neutral pH, the concentration of H plus or OH minus is these are very low. So, under such low concentration, means either mechanism or this mechanism or that mechanism is difficult to operate. So, maybe there is a very little amount of H plus which tends to protonate this oxygen, but since concentration is less, that contribution is also less. In the same way, since OH minus is also less, so contribution of this step is also less, but it is happening because there is although it is very low, but it is finite, it has got some finite value. So, with that finite value of OH minus or H plus, this reaction proceeds, this step proceeds, but with rate much reduced. So, in the vicinity of pH 7, we see that it is flat, it increases further in the right hand side and also in the left hand side, like the example I gave in the earlier slide, that that for hydrolysis of ester catalyzed by acid or base. In the same way, for uncatalyzed reaction, like there is one step, it could happen over here, okay, but that happens very slowly. That is why, because H plus and OH minus is less, okay, at pH 7. So, that is why it is minimum, rate is minimum. Okay. And you can study this mutarotation reaction polarimetrically. Okay. So, in one case you use acid, another case you use base, and the third case you do not use acid or base, or basically you use a pH 7 buffer maybe, where the concentration of H plus or concentration of OH minus will be very low, and you can polarimetrically study and you can find out the rate, because with time your optical rotation changes, and from this change in optical rotation you can find out this observed K. Next is there is another reaction which is Imin formation. Okay. So, you see, if you plot log K observed versus pH, it is found to be to maximize around pH 4.5 to 5. So, optimum pH is around 4.5. So, if you go either way, like if you go below 4.5 or maybe above 4.5, reaction has been found, a rate has been found to reduce. So, what happens is that in presence of an acid, that is in presence of H plus, so this forms RnH3 plus. So, it is inactive, although it is a nucleophile, but it is inactive. But in presence of H plus, this carbonyl, it gets protonated and it is further activated, and then RnH2 attacks this one to produce this one, okay, and then it equilibrates here, and then this bond, this bond cleaves. This is a leaving group, OH2 plus is a good leaving group, so it cleaves, okay, and then it forms Imin, okay. It has been found to have, rate has been found to have maximum value when we are in the vicinity of 4.5 to 5, okay. So like unlike this one where you are getting a plateau around 7, although in this case you are getting a minimum around 7, but here the maxima you are getting at at a value which is different from 7, that is 4.5 to 5, okay. So this is another example of acid catalysis, and in C acid catalysis and also the effect of pH, okay. So from these 3 examples we can say that the reactions which are catalyzed by acid, H plus, these may have strong dependence of pH, okay. Okay, so next let us look into mechanisms of acid catalysis, okay. So one is which is called a specific acid catalysis, and the other one is called the general acid catalysis. For the first one, that is specific acid catalysis, what is happening? A proton is transferred to the reactant in a rapid pre-equilibrium like this, okay. This is your substrate or reactant, HA. So this this HA, this proton is transferred to this S, producing SH plus, okay. And then and this is a fast equilibrium, this equilibrates very fast, okay. And then once it is formed, this SH plus, it slowly gives rise to products, okay. So this is fast equilibrium, then slow product formation. So this is the rate determining step, okay. And for your general acid catalysis, okay, so in that case the reverse is the situation, that proton transfer occurs in the rate determining step. So there is the equilibration step, is the slow step, and then once SH plus is formed, it produces, it gives rise to products very fast, okay. So for specific one, it is the first fast pre-equilibrium, and for the general acid catalysis, it is the slow, equilibration, slow proton transfer, okay. So these are the two situations. One is your specific acid catalysis, and other one is the general acid catalysis, okay. So specific acid base catalysis. So let us look into it again. It is generally observed with electronegative elements, as I told you at the very start of our discussion, that you see here for your specific acid catalysis, this one is the fast, that is proton transfer is fast. So proton transfer fast means it is expected to involve oxygen, nitrogen, okay, and the proton transfer is very fast. So this is the equilibrium constant, and the process, this pre-equilibration is very fast. And the second step is the rate determining step. It may be mono or maybe unimolecular or maybe bimolecular. So for your unimolecular case, EH plus, okay, with rate constant K1 produces your product, and then in presence of water it gives rise to products, means in presence of water, of course. So and it is a slow and unimolecular mechanism, okay. For the other one, you see that water is involved here in this step, in this slow step. So, that is why it is a bimolecular, or it is called the A2 mechanism. Okay. So, for your rate, you see that V is equal to K1 into EH plus, K1 into EH plus, and EH plus means, you see, K EH plus means it is you see that equilibrium constant K is equal to your concentration of EH plus divided by concentration of E and concentration of HA. Okay. So, EH plus is equal to K into E into HA. Okay. So, you just plug in this, okay. You plug in this to your expression, that is V is equal to K1 EH plus, which is equal to K1 into K this one will have, you know, EH plus into E minus, of course. So, I missed one thing. So, this is E minus. So, Kk into E HA divided by A minus. Okay. So, this is the rate expression including your equilibrium constant. Okay. So, so since Ka is H3O plus A minus divided by HA, so you can plug in this, over here, and ultimately you get that V is equal to K1 into K divided by Ka into E into H3O plus. So, you see that this rate is strongly dependent on H3O plus concentration, that is your acid concentration or the concentration of hydronium ion present in the in the solution, in the reaction mixture. Okay. Okay. So, we have seen that your rate is dependent on the rate constant for the slower one, then equilibrium constant for your EHA, EH plus A minus equilibrium, and also the acid constant Ka, and you see that V is proportional to H3O plus. So, V is proportional to H3O plus concentration. Okay. Next, let us look into hydrolysis of acetals, unimolecular mechanism. That this is the acetal, then in presence of H plus, of course, aqueous acid, you see that acetaldehyde, okay, gives rise to, I mean, acetal of acetaldehyde means, I mean, benzaldehyde, sorry, it is not acetal, it is benzaldehyde. So, benzaldehyde acetal, then in presence of H plus produces benzaldehyde and 2 molecules of CH3OH, and you see that in presence of H plus, the K observed, as H plus is increased, here K observed is also increased. Okay. It is not exactly linear, although it is just giving you an idea of whether K observed is increasing or not. You can also have plotted, you can also plot log K observed as a function of, you know, pH. Okay. So, it is you know, increasing. Exactly how much it is increasing, what is the exact slope, we are not looking into it. You see that K observed is proportional to H plus concentration. Okay. And what is the mechanism? Mechanism is that you have got the acetal of biacetal. Okay. So, it is biacetal of benzaldehyde in presence of H3O plus, it is a fast equilibrium, and then slow, you know, this rupturing of this bond, okay, produces your produces your products. So, again what you do, if you plot K observed as a function of your buffer concentration, although keeping your pH constant, you won't see any change in your K observed. So, that means it strongly depends on okay, strongly depends on, you know, this hydrogen ion concentration. So, this is A1 mechanism. A1 mechanism means your this one, first pre-equilibrium followed by slow decomposition. So, here it is first pre-equilibrium followed by slow decomposition to your products. Okay, so, in presence of acid, this is your acid. So, here protonation takes place and then the reaction proceeds like this. Okay. Next, specific acid catalysis, and it is A2 mechanism, hydrolysis of ethyl acetate. So, ethyl acetate, so again go back to this one, you know, slow equilibration, fast product formation. So, this one in presence of H3 plus. So, this is your slow equilibrium, fast then slow, this is your fast equilibration A2 mechanism. It is a bimolecular, of course, bimolecular A2 mechanism means here it is a bimolecular one. This one I am looking into this one, see, it is, you know, product formation, and here you see that H plus H2 K2 product formation is a slow, slow, and it is A2 mechanism. This is unimolecular, this is your bimolecular. So, we are now concentrating on bimolecular. You see that it is fast protonation followed by your bimolecular, you know, bimolecular slow decomposition. Okay. So, hydrolysis of ethyl acetate is of such kind. Okay. Now, specific base catalysis, there is another example, retroaldol reaction of this one, in presence of base it produces acetone. Okay. So, it has been found that rate constant K is proportional to OH minus concentration, okay, and it increases linearly, there is a positive slope. Like this reaction, this one, it is an H plus catalyzed, this is OH minus catalyzed, it is a specific base catalysis. So, what is the reaction? What is the reaction mechanism? In presence of base, it is an equilibration, it is a fast equilibrium. So, this proton is snatched by B minus producing Hb, and then the slow decomposition. So, this electron, this charge is backfired, and then this bond is ruptured. So, producing these two, and then ultimately from water it takes up one proton to give rise to 2 molecules of acetone. Now, rate of reaction is half deacetone dt, that is the rate of formation of acetone, and ultimately if we follow this expressions, K equal to 2 into Hb divided by 1 into B minus, and then concentration of 2 will be, this one is 1, this one is 2. So, concentration of 2 has got this expression, and considering acid base equilibrium in water, B minus plus water, Kb, Hb and O minus. So, if we plug in the appropriate numbers, so expression over here, then we will be seeing like the other one, that is your hydrolysis of ester. Let us go back to that slide also. You see that V is proportional to H3 plus. In the same way, here we are also getting your V is proportional to OH minus. Okay. So, it is a specific base catalysis where we are seeing that your reaction rate K observed is very much proportional to OH minus. Okay. Now, general acid base catalysis is observed in a majority of enzymatic reactions. General acid base catalysis should be distinguished from specific acid base catalysis. Okay. For general acid base catalysis, the buffer aids in stabilizing the transition state via donation or taking out of proton. Okay. Thus, the rate of reaction depends on the buffer concentration for general acid base catalysis and also on the appropriate protonation state. Okay. General acid catalysis is a process in which partial proton transfer from a Bronsted acid which can donate protons lowers the free energy of transition state. General base catalysis, process in which partial proton abstraction by a Bronsted base, that is which can combine with a proton and lowers the free energy of transition state. Okay. And general acid base catalysis, in case of a general acid base catalysis, you know, I mean for a general acid base catalysis, a combination of both can also happen. Okay. General acid base catalysis, it is a general acid catalysis and it is a base catalysis. So, for general acid base catalysis, both of these two can happen. Okay. Next, general acid base catalysis, proton transfer is the rate determining step. Okay. As for example, hydrolysis of ortho esters. Okay. In presence, this is 3, number 3. So, in presence of H plus, it gives rise to this, and this type of reaction has been studied in a series of buffers, that is phenol phenoxide buffer, and it has been found that rate increases with buffer concentration even when the pH remains constant. Okay. So, your rate of reaction rate is K corresponding to water, rate constant for water, then rate constant for H3O plus, and then rate constant for the one which is coming from pH-OH, that is phenol. Okay. So, and also the concentration of phenol. So, these three are the contribution of the different constituents, that is water, H3O plus, and also from your buffer. Okay. And this is the reactant, but this K part has got the contribution from your water, that is which is present in large excess, and also if there is some H3O plus ions present, and also on these 3. But here if we plot V versus buffer concentration, you see that it starts from somewhere over here. If you increase the buffer concentration, rate has been found to increase from here to here. Okay. So, this part you can call the residual one, which is the contribution from your H3O plus part and also from your H2O part. Okay. Next slide, general acid base catalysis. The reaction rate is dependent on all the acid bases present in a mixture, as I told to you that this is maybe this is a base, this is acid, and this is also an acid. So, that is why all of contribution from all of them is in action. Okay. So, for general acid catalysis, contribution of all the HAs present, and for general base catalysis, contribution from all the bases present in the mixture. Okay. So, observed K is the contribution from your individual acids or individual bases. Okay. An example of general base catalysis, you see that bromination of this one, dibromination, second bromination in presence of base. So, observed rate constant has been found to increase with your buffer concentration even if you fix the pH. So, this reaction rate is dependent on the buffer concentration at constant pH, and there is also there is a contribution of OH minus and H2. So, this part is accounting for this line, that is there is also contributions from OH minus and water. Okay. Thus, for general acid base catalysis, so what happens that rate of reaction depends on the buffer concentration as well, okay, which is evident from your this plot. So, this part is from your from your this last sentence, that is there is also contributions from OH minus and H2O. Now, reaction mechanism goes like this, that is reaction mechanism for this particular reaction, you know, it is shown over here that it is a slow abstraction of proton, and then it has got the resonance hybrid, then in presence of bromine, you know, this minus attacks the bromine to snatch this Br, and Br minus is, you know, displaced. Okay, so rate of disappearance of Br2, which has got the contribution from your water, okay, it has got the contribution from your OH minus, okay, and it has also got the contribution from your this one. Since it is a general base catalysis, so this base is also effective over here, okay. So contribution, that is your K arising out of, that is the contribution of this K due to this Cl CH2COO minus, or maybe the contribution of this contribution to your K, overall K for this water, and this is your contribution to overall K for your OH minus. Okay, so these are individual contributions. Okay. Okay, next summary. Specific acid base catalysis. Okay, so you see here S plus HA is a fast equilibration, SH plus A minus. So the mechanism is A1 mechanism, that is unimolecular mechanism, SH plus slow giving rise to products, or bimolecular mechanism, SH plus water, two products, it is a slow process. Okay. So for specific acid or specific base catalysis, you see that rate of the reaction, velocity of the process has has this kind of expression, and where you can see that your velocity is proportional to H3O plus, or maybe velocity is proportional to OH minus. Okay. So that means it has got the direct dependence on your acid concentration or base concentration. So it is thus it is specific acid or specific base catalysis. Okay. General acid base catalysis, on the other hand, it is slow equilibrium and then fast dissociation to products. Okay. And here your overall the velocity of the reaction, it is from your it has got the contribution from various components, okay, like H3O plus, H2O, then HA, okay, or maybe with bases it is OH minus, H2O and A minus, okay. So it is basically sum over various factors, sum over various various concentration terms, okay. Now when the concentration of this H3O plus or OH minus, so you see it is these are large, then contribution from other acids bases are negligible. That means in case of general acid base catalysis, we see that the overall velocity of the reaction is proportional to contribution coming from H3O plus, or plus contribution coming from water and also from the HA, that is from the acid. But suppose out of these three, if we make this one large, then contributions of these are negligibly small. Or if you make this OH minus very large, contribution of this one is very large, then contribution of other parts are negligibly small, and the kinetics resemble specific acid base catalysis. So then your expression is converted, that is this expression is converted to this expression or maybe this expression, depending on whether it is a base catalyzed, I mean acid catalyzed, or it is a base catalyzed cases. Okay. So that's why general acid base catalysis usually occurs in neutral pH or maybe around pH neutral situation. Okay. So that means you can convert a general acid base catalysis to a specific acid base catalysis by taking your base or your acid to a large extent. That is, if you can make their contribution large, then the contribution from water or contribution from HA or maybe contribution from A minus, these are becoming negligibly small, and and your situation gets converted from general to specific. Okay. General acid catalysis and the Bronsted relation. The effectivity of a general acid catalyst depends on the acid strength, okay, and that is the Bronsted relation. I mean, we relate this to Bronsted relation, that is log KHA is equal to alpha log KHA, that is your equilibrium constant plus some constant. So, KH is the rate constant for the catalytic step, that is the step which is thought to be the the step where wherein your catalysis occurs. KH is the dissociation constant of the acid, alpha is the Bronsted coefficient, okay, and normally it is in the range of 0 to 1, 0 is less than alpha is lesser than 1, and this indicates the sensitivity of the catalytic step when acid strength of HA, that is pK, changes, okay. So, it is a marker for the sensitivity, okay, and it is called the Bronsted coefficient, okay. So, this is the expression, that is log KHA is equal to alpha log caps KHA plus constant. So, we will try to use this expression. Example, this is a reaction. So, look into this reaction, this is slow protonation, then in presence of water fast dissociation, fast product formation to give you this one, okay. If you plot log KHA against log equilibrium constant, okay, that is this expression, if you plot this with this, okay, then you will be getting alpha from your slope, and alpha indicates to what extent proton is transferred from acid to the substrate in the transition state, okay. So, that is if it is slope is unity, then situation will be 1, if it is 0, then situation will be another, if it is in between like 0.5, then situation will be something else also. So, let us look into that. When alpha is equal to 1, okay, so every change in acid strength fully affects catalysis. That means, if alpha is 1, that is log KHA, it is a rate, this is the equilibrium constant. So, there is just 1 to 1 correspondence, okay. So, every change in acid strength fully affects catalysis, okay. The proton is almost completely transferred to substrate in the transition state, you can think in that way. Alpha is equal to 0, the reaction is insensitive to changes in acid strength, okay. Alpha is equal to 0 means log KHA is just constant, okay. So, all acid catalyze all acid catalyze the reaction equally strongly, okay. That means there is no difference in pK, there is no difference with respect to pK, any acid can do the reaction. That is why it is called all acids catalyze the reaction equally strongly. So, log KHA is constant, okay. The proton is hardly transferred in the transition state of the reaction, okay. And if it is 0.5, that means if it is log KH is equal to 0.5 log capital KHA plus constant, then it is called the proton is transferred halfway between the acid anion and the substrate in the transition state. So, transition state is symmetrical, it looks like this, okay. And there is also a similar relation for general base catalysis for Bronsted, okay. So, it is log Kb is equal to minus log KHb plus constant. So, the coefficient beta has the same meaning as alpha for the general acid catalysis, okay. So, general and specific catalysis, why is there sometimes general and sometimes specific acid base catalysis. Let us think in terms of pH. H plus and OH minus are very low in neutral solution, whereas HA or B can be high. So, this may promote general catalysis. Rate of proton transfer, H transfer to and from C, I mean H transfer to carbon atom or from carbon atom is slower than transfer to nitrogen or oxygen or transfer from nitrogen or oxygen, etc. So, this may promote general catalysis. Stability of intermediates play important roles, as for example, compare hydrolysis of orthoesters and acetal. Okay. And this is the example. This is the example where you see that acetal and orthoester. Okay, as I told you that compare hydrolysis of orthoester and acetal. So, stability of intermediate plays very important role. Okay, so if you compare these two, you can probably think of that 1C is more stabilized than 2C. You see this one. This is 2C. This is 1A, 1B, 1C, 2A, 2B, 2C. So, 1C is more stabilized than 2C. Okay. So, protonation becomes the rate limiting step. So, this is general acid catalysis. Okay. So, what have we learnt out of this? That this acid base catalysis is a very important phenomena. It is observed not only in case of general chemical reaction, but also for the biological reactions as well, and which will take over, which we will talk about in the next lecture. But the thing is that this has got, this acid base catalysis has got two kinds. One is specific acid base catalysis, and the other case it is general acid base catalysis. So, specific acid base catalysis occurs when we take your acid or base in large extent. So, contribution of these parts, other part, that is from water or from HA, becomes negligibly small, and then it is a general acid base catalysis is converted to a specific acid base catalysis. And also in pH neutral condition, the general acid base catalysis is promoted. So, it is very important that under what condition, what pH condition or what buffer condition you are carrying out your reaction is very important. Okay. So, we have learned here the specific acid base catalysis, general acid base catalysis, various mechanisms, and also the rate schemes, and also the effect of pH and the effect of buffer concentration as well. So, in the next lecture we will talk about this specific or general acid base catalysis for your biological systems, biological reactions, and also your metal ion catalyzed reactions. Okay. So, that is all for this lecture. So, thank you.